Okay, so yesterday we looked at explaining the acidity of carboxylic acids. And carboxylic acid, even though it is a weak acid, it is the most acidic among all other organic functional groups like alcohol and water, phenols as well, okay? Something is not, hold on. How do I, okay. Plug in, how do I plug in? Sorry, hold on, yeah. Where I was saying, okay. So if we looked at the acidity between these three functional groups, carboxylic acid, phenol, and alcohol, carboxylic acid is the most acidic because there is a delocalization in carboxylic acid that makes it more acidic, okay? So when we look at the carboxylate ion, the reason why carboxylate ion is important is because during ionization, ionization is usually our key indicator for the acidity of that substance. If there are a lot of ionizations, you release a lot of hydrogen ions as well as your anion. In this case, for carboxylic acid, it's carboxylate. That means it is acidic, okay? If you don't have a lot of ions, less acidic, okay? For carboxylate ion, we saw that the negative charge that you would have thought belonged to the oxygen down here is actually being shared with the COO part of the carboxylate, okay? So this is your delocalization, okay? Because the charge is not fixed. The charge is being delocalized throughout the COO part only, not the alkyl group, okay? Another thing is that the pi bond that you thought belonged to C double bond O is also being delocalized, okay? The pi bond is being delocalized throughout the COO part of the group again, okay? The reason for this delocalization is this, okay? The pi orbitals of the C double bond O align with the orbital of the lone pair of that oxygen with the negative charge. So because they overlap or they are parallel, they form a delocalized system, okay? Don't forget in phenol, you also have some sort of delocalization where, same thing, the lone pair of the oxygen aligns or overlap with the p orbital in the benzene ring, okay? I'm not drawing it. It's not the correct drawing, but yeah, okay? And in alcohol, for the alkoxide, there is no delocalization, okay? No delocalization at all. That's one. The second reason is also because of the presence of the alkyl group. Alkyl group is an electron donating group. It pushes electron density towards the oxygen. That's why you see this green arrow. It pushes electron density towards the oxygen. The oxygen is already negative. So if you push, if you push a negativity to someone who is already negative, then that person becomes more and more unstable. Okay. Right. So previously we were looking at the difference in acidity for different functional groups. Now we're going to focus on the acidity of different carboxylic acids, okay? So they're all the same carboxylic acid, they have the same functional group, but they have slightly different constituent. Constituent means one or two of the atoms are different, okay? So we will use the concept of electronegativity to explain the acidities of chlorine substituted ethanoic acid. So that's for the second part, okay? As mentioned yesterday, the strength of a carboxylic acid is affected by the nature of the substituent group. So substituent group is an atom that sits in your carboxylic acid, okay? So there are two types, the electron donating and the electron withdrawing. They have completely opposite effect. We're going to look at the electron donating group first, okay? What electron donating group does is that it decreases the acidity, okay? For a reason that we're going to look at after this. So before I talk about the explanation, I'm just going to show you these two carboxylate ions of a carboxylic acid, okay? So this is a propanoic acid. Do not forget to include that carbon of the COO. Sorry, this should be a propanoate ion, okay? Not propanoic acid. This is a propanoate, and the one on the right is an ethanoate ion, okay? Both of them have the same delocalization. So you cannot say that the delocalization of propanoate is weaker than the delocalization of ethanoate, okay? So you do not talk about the delocalization because both of them have the same exact delocalization. The one that we're going to look at is the substituent, okay? What sits next to the COO minus, okay? So here we have an alkyl group sitting on the ethanoate, and we have an ethyl group sitting on the propanoate, okay? The green one. So basically, both of these ions are already negatively charged ions, okay? And we say that alkyl is an electron donating group. However, these two are two different alkyls, okay? Propanoate, well, as you can see, it has an ethyl group, and ethanoate, it has a methyl group, okay? So methyl group, I will draw it in terms of arrow to show you the effect of the electron donating group, okay? So a methyl group, because it only has one carbon, so it only donates, you know, a small amount of electron density to the negative ion, okay? So I use one arrow. For propanoate, you have an ethyl group. So ethyl group is bigger, so it has a bigger electron donating effect, okay? So I will draw it by two arrow, okay? The number of arrows is not really, it's just arbitrary, okay? One arrow means small effect, big arrow means big effect, okay? So you can see, because an alkyl group donates a small electron density, okay, to the already negative ion, so it is, okay, less stable, right? Just like that. For propanoate, the ethyl group is a bigger alkyl group, so it donates a little more of electron density, okay, to the ion. So the propanoate ion becomes very unstable, more unstable than ethanoate, okay? Remember that both of them are unstable as it is, but propanoate, seeing that it has a bigger electron donating group, it is much more unstable than ethanoate, okay? So we're talking about relative instability here. Right? So increasing chain length of alkyl pushes on the COO minus ion, making it more negative and less stable. So the idea is, the longer the alkyl group or the longer the chain of your carbon, the bigger electron density is being pushed, therefore the less stable your anion will be. Okay, so if your anion is less stable, it is less likely to be formed. So you have less ions, therefore less acidic. Okay, so I try to avoid the word make the acid less strong. I would say less acidic. Okay, so this is why here you see propanoic acid is less acidic than ethanoic acid. I would say propanoic acid is more unstable than ethanoic ion. Okay, both of them are still unstable. So remember, the bigger the alkyl group, the more unstable your negative ion would be. Okay, so this is a few more examples. Your methanoic acid, ethanoic acid, and propanoic acid. So all of these have the same COOH, so you cannot really compare the COOH, okay? What you can compare is the substituent, okay? So if you look at the methanoic acid, now the pKa tells you the lower the pKa is, the more acidic it is, okay? So my screen is not changing. I just realized that. Hold on. Let me try it again. Okay, right. So if you look at the pKa value, the pKa value has the opposite effect of Ka. Okay, the lower the pKa is, the more acidic. So this is most acidic methanoic acid, and your 1, 2, 3 propanoic acid is the least acidic. Okay, remember that they are all still weak acids, right? I try to avoid using the term methanoic acid is stronger acid than propanoic acid because they are all weak acids. Okay, right. So if we look at the constituent, okay, on each of these acids, okay, let's have a look at methanoic acid first. Okay, so methanoic acid, it forms methanoate ion. Okay, you don't see it here. You don't see it forming methanoate ion, but if you want me, I can draw it for you if I can find space. C double bond OOH minus. Okay, now if you look at the methanoic acid, the only thing that is attached to that COO minus is hydrogen. Hydrogen has no electron donating nor electron withdrawing effect. Okay, so the COO minus is just like that, right? If you look at the ethanoate ion, same thing, you have a methyl group pushing electron density, pushing negativity to that already negative anion. And then the last one, you have a C2H5, okay, pushing a bigger electron density to your already negative ion. So you can see that the anion of the propanoic acid is the least stable, okay, compared to the anion of the methanoic acid, which is methanoate ion, where you don't have an electron donating group, but it is the most stable among all these three acids. Okay, we're not talking about methanoic acid versus other functional groups like phenol or alcohols. Okay, but still methanoic acid will be much stronger than phenols and alcohols because methanoic acid falls under carboxylic acid. Any carboxylic acid will be more acidic than phenols and alcohols. Okay, I hope that is clear to you. The second type of group is the electron-withdrawing group. Okay, so electron-withdrawing group has the opposite effect. You are now taking electron density away from the COO minus. Okay, in electron donating, you see the arrow is being donated to COO minus, but in electron withdrawing, you will see the arrow being drawn opposite direction. I'll use blue. Okay, so this time the arrow is going away from the COO minus. But who is pulling this electron density? It's the chlorine. So it is like a chain reaction. The chlorine is pulling the electron density from this carbon-chlorine bond, and then it is again pulling the electron density from that carbon-carbon bond that is attached here. Okay, so it is a chain reaction. The reason why chlorine pulls can take away electron density is because chlorine is one of the most electronegative element. I know fluorine, oxygen, and nitrogen is like one of the most electronegative, but chlorine is also considered as a highly electronegative atom. And if you remember from your AS, electronegativity means the tendency of the atom to pull the bonding electrons to itself. Okay, it doesn't completely steal the electron density, but it just make it closer, pull it closer to itself. So if you're wondering here, if chlorine is pulling away the electron density of the COO minus, will COO minus lose the negative charge? No, the negative charge will still be there, but much weaker. Okay, think of it as someone being a person, okay, in this case COO is negative, okay, and then another person is taking away your negativity, so you become stable, right? Okay, you're a negative person, one person, another friend comes to you and try to remove the negativity inside of you, trying to lessen the negativity inside you. Okay, it doesn't mean that you are completely not negative now. Okay, you still have some sort of negativity, but less. Okay, so that's what chlorine is doing to COO minus. It reduces the electron density. It makes the COO minus a little bit stable. Okay, not completely, but just a little bit stable. Okay, so electronegativity chlorine atoms withdraw the electron density. Okay, please use that word electron density. It's not withdrawing negative charge, it's not withdrawing electron completely, just the electron density. Okay, what's electron density here? It's just like you are pulling some of the electron clouds, but not all. Okay, so when you withdraw electron density from a COO negative ion, you make the COO negative ion less negative. Okay, and if you make a negative ion becomes less negative, that means that person is a little bit more stable. Okay, so that's why if you want to compare, this is called a chloroethanoic acid. Okay, chloroethanoic acid name, quite simple. You look at the, sorry, this is an chloroethanoate because it's an ion, so I wouldn't call it an acid. Chloroethanoate. Ethanoate is because you have two carbon groups and then there's one chlorine. Okay, chloroethanoate is more acidic than ethanoate ion. So if I draw ethanoate ion, normally it would be like that. Okay, so ethanoate ion, you have the opposite effect. The CH3 is donating electron into the COO minus. Okay, but for chlorine, it is taking electron away from the COO minus. I hope you can see the difference in the arrow being drawn here. Okay, now we're going to look at the different chloroethanoic acid. Okay, both of them contains two carbons, so they're all ethanoic acid, but this is a trichloroethanoic acid, dichloroethanoic acid, and a chloroethanoic acid. Okay, so they have the same number of carbon. The only difference is the number of chlorine. So if I just highlight this for you, there's 1, 2, 3 chlorine, 1, 2, and there's only 1. And by looking at the pKa value, the smallest pKa value is the most acidic. So the trichlor is the most acidic, and the, what's happening with my, okay, and the chloroethanoic acid is the least acidic. Okay. Reason, I hope it is self-explanatory that you have 3 electron withdrawing group, so it withdraws a lot more of your electron density. So your ion will be the most stable here. Okay. In your chloroethanoic acid, which with only 1 chlorine, okay, there's only 1 atom or 1 group that removes your negativity. Okay, so it's another way of seeing this is like having 3 friends trying to remove your negativity, trying to cheer you up, versus one friend to remove your negativity or trying to cheer you up. Okay, you know, if you think about it psychologically, then of course maybe some of you prefer to just have one friend and not three people to come and comfort you. But the idea, the analogy is there. Okay, more people reducing or more electronegativity. More negativity is removed from you, the more stable you will be. Okay, less negativity removed from you, the least stable you will be. Okay. So the greater the electron withdrawing effect, the stronger the acid. Okay, so that's why trichloroethanoic acid is the most acidic, because you have more electron withdrawing group. Moving on. This time we have the same ethanoic acid. Okay, but all of them have 2 carbon, but the only difference is the halogen. Okay, fluorine, chlorine, bromine, and iodine. Hold on, yeah, let me just check if you have this in your notes. Yeah, you have this in your notes. Okay, so if we look at the pKa value, they're not so very different, but you can conclude something. The one with the fluoroethanoic acid is the most acidic. Okay, and the one with the iodine or iodoethanoic acid is the least acidic based on the value. Okay, explanation. Fluorine is the most electronegative. Okay, so with poles, I will draw 4 arrow. Okay, just for comparison. And then iodine is the least electronegative. So that means iodine is not as strong at withdrawing the negativity from the COO minus compared to fluorine. Fluorine is great. Fluorine is really great at removing negativity from your COO minus, hence the 4 arrows. Okay, that means chlorine will have 3, bromine will have 2. Again, I remind you the arrows do not indicate anything, but that's just showing you the relative size. Okay, more arrow, bigger effect. Right. Now, I noticed that the drawings given here are actually the acid, not the anion. Okay, but when it comes to explanation, you will talk about the anion. Okay, the stability of the anion. Here is another example where it's the distance factor. Okay, if you look at both of them, this is 1, 2, 3. It's a propanoic acid. This is 1, 2, 3, 4. Okay, so it's a butanoic acid. So it's about the distance of the chlorine, the distance of the electronegative group. The closer the electron withdrawing atom is to your COO minus, the bigger the effect of withdrawing electrons. The further away, the smaller the effect. Okay, so if you look at this chlorine, if I try to draw it out, 1, 2, 3. Okay, then you have a chlorine here, right? The other one is 1, 2, 3. You have a chlorine here. Okay, so if you look at the blue anion on the left side, you can see that the chlorine is like 2 carbons away from the COO minus. Okay, so that means it's not close, but it is closer than the orange anion. Okay, here you can see that the chlorine is like 3 carbons away from the COO minus. Therefore, the effect of withdrawing electron density is weaker because it's further away. Okay, so I hope that is quite obvious. And so that means the chlorine that is closer to the COO group is more acidic because it is more effective at withdrawing or pulling electrons away from the COO minus group. Okay. This is another slide showing you the example that we were looking at previously. Okay, so to name the molecule, of course, you take the carbon of your COOH as your first carbon. 1, 2, 3, 4. Okay, so that's why we call it 4-chlorobutanoic acid. 1, 2, 3. 3-chlorobutanoic acid, that's where your chlorine is sitting. 1, 2. 2-chlorobutanoic acid. Remember, when naming, you must always count the carbon of the COOH, and that carbon is always number 1. Okay, it will be given priority number 1. So you can see that this chlorine is the closest to the COO minus group, therefore it is the most acidic. Okay, it has the smallest pKa, most acidic. Don't worry about the slide because the same explanation applies in your notes. Okay, it's the distance factor. Okay, let's see. Right, so that's some acidities of your carboxylic acids explained. Okay, now I'm just going to briefly talk about the chemical reactions of carboxylic acids. Okay, carboxylic acids react just like your normal acids. Okay, so that means it can, although not as vigorously because it's a weak acid, so it's much more, it will be a much more like a more gentler reaction, or a milder reaction because it's weak. But my point is that carboxylic acids can react with metal, bases or alkali, and carbonate. Okay, so when it reacts with metal, it will form salt and hydrogen gas. When it reacts with alkali, it will form salt and water. When it reacts with carbonate, it will form salt, water, and carbon dioxide. The salt, make sure that you know it is made up of the ethanoate ion. Okay, so if you use sodium, it will be sodium ethanoate. If you use sodium hydroxide, same thing, sodium ethanoate as well. Okay, if you use a butanoic acid, the salt will be sodium butanoate. Okay, just make sure that you know how to write down the formula. Okay, it's when a carboxylate ion is when you lose the hydrogen that is attached to the oxygen here. Okay, you lose that hydrogen and then you're left with that. The R group represents any alkyl group. Okay, so some of these reactions are reactions that you can observe, like hydrogen gas. You can see effervescence. You can test for hydrogen gas. Okay, carbon dioxide. You can see, sometimes you can see bubbles of gas being produced. And you also can test that gas. Okay, so this reaction is sometimes used as a test for carboxylic acids. Okay, for example, if you want to differentiate carboxylic acid and alcohol, okay, alcohol will not react with carbonate, but carboxylic acids will react with carbonate. So that's how you use this reaction as a test. Okay, so whatever reaction in organic chemistry, I'm sure I've already mentioned this to you, if you can see or observe something, this reaction can be used as a test. Okay, even a reaction as simple as bromine, because bromine is orange brown in color. When the reaction occurs, it becomes colorless, decolorized. Okay, so you may have come across the reaction of bromine being used as a test to confirm. Okay, now you already know that bromine or chlorine can react with a few functional groups like alkanes, arenes, which is your benzene, that is including methyl benzene, phenols. Don't forget, your bromine can also react with phenols, but all this reaction occurs at different conditions. okay? But you can tell if there is a reaction occurring or not, because if there was a reaction occurring, your bromine will turn from brown to colorless, or you say the bromine is being decolorized, okay? We only have 6 minutes left, so I will not go further, but for the next lesson, we're going to look at the oxidation of some carboxylic acids, okay? Now, if you remember from AS stuff, okay, primary alcohol can be oxidized, okay, I'm just going to write that, into an aldehyde first, and then carboxylic acid, final. Okay, we say that in AS, the carboxylic acid can no longer be oxidized. Okay, but you will learn that, hold on, in A2, there are some, okay, actually only 2 carboxylic acids that can be oxidized further, okay, but not all, only 2. That is methanoic acid and diethanoic acid, okay. In AS, we say that the carboxylic acid cannot be oxidized further, but actually in A2, you will learn that 2 carboxylic acids specifically can be oxidized further into carbon dioxide, okay. Right, so I guess that is all for today, because there's nothing much that I can talk about without going into depth of the section. Right, we have 4 minutes left. Do you have any questions?